Hello students, and welcome to this video on comparators, encoders, and then multiplexers to follow. So first of all, comparators. The basic function of comparators is to compare the magnitudes of two binary quantities to determine the relationship between those quantities. In the simplest form, comparator circuit determines whether two numbers are equal. Okay, so it just compares the two numbers and sees which one is bigger. We look at equality, inequality, and then the 4-bit magnitude comparator. First of all, in equality, the exclusive NOR gate can be used as a basic comparator because its output is a 0 if the two inputs are not equal and a 1 if the input bits are equal. So now we see how exclusive OR gate. So see if the two bits are equal, it's a 1, and if they're not equal, it's 0, and then the 1 and 1 and 1. So we use an exclusive NOR gate to see if two bits are equal. Now we want to compare more than 1 bit. We want to compare 2-bit numbers. So for this, we use two NOR gates and an AND gate. So one of the NOR gates compares the least significant bits, A0 and B0, and other NOR gate compares A1 and B1 together. So if they are both the same, they're a 1 and a 1, then this will be a 1 as well. But if this one is not the same, this one is is the same, so this is 0 and 1, which would be 0, so that indicates inequality. So it'll only be high, the output of this AND gate, if all the bits are the same. Now we're looking at inequality. So in addition to equality output, many IC comparators provide additional outputs that indicate which of the two binary numbers are being compared is the larger. So that is, there is an output that indicates when number A is greater than number B, and an output that indicates when number A is less than number. So this is then shown in this IC. So you have your 4-bit number from least significant bit to most significant bit, and the number it's being compared to from least significant bit to most significant bit. And on the outputs, you see if A is bigger, if A is exactly the same as B, or if A is smaller than B, then the respective outputs would be high. Okay, so that comparator works in the way it determines the inequality between numbers A and B. You first look at the highest order, A3 or B3, and see which one is higher. So if A3 is bigger than A3 is 1 and B3 is 0, then number A is definitely greater than number B. And if A3 is smaller than B3, or 0 and a 1, then number A is less than number B. And if they are the same, then you will look at the next bit, i.e. you will compare the B2 bits. This just makes the operation a lot easier if you have large bit numbers, because if the most significant bit is a 1 and the other significant bit of the number it's being compared to is a 0, then that number is definitely greater. So you don't have to compare the whole number, you just compare the most significant bits and then move down until one of them are greater or smaller. And this is basically what's saying here. So we just go starting from the highest order bits and moving down to the low order bits, and then see which number is bigger, which number is smaller, or if they're all the same. Now we look at the comparator IC. I think the IC is given in your study guide. And if you look at the IC here, that's obviously VCC, that's ground. And then you have your input bits, A0, A1, A2, and A3. And the number it's being compared to, B0, B1, B2, and B3. And then you have these outputs. Here you have if A is smaller than B, if A is equal to B, if A is bigger than B, if A is bigger than B, output, and if they're all the same. And then these are for the input bits, are for the cascading input. So if you have, let's say you want to compare an 8-bit number, then you would cascade the bits into these as inputs, and then you would have the outputs, i.e. these outputs. So the inputs would be for cascading of comparator ICs if you want to compare a number that's more than 4 bits. And now we come to decoders. So decoders is a digital circuit that detects the presence of a specific combination of bits. And so now we come to these basic binary decoders, and we'll build up to a BCD to 7 segment display decoder. So now we want to, suppose we need to determine when a binary 1001 occurs on the inputs of a digital circuit. An AND gate can be used as a basic decoding element because it produces high output only when all the outputs are high. Therefore, we can make sure that all the inputs to the AND gate are all high when the binary number 1001 occurs. So this can be done in this way. So we have a 4-input AND gate, and if that one is 1, if that was 0, we invert it, so it becomes 1. So only when this code comes up, and only when this code comes up, this gate will be a high. Okay, so if it's a 1101, that would go inverted, would be a 0, and it would not be 0. It would be 0, sorry. So the only when you have 1001 on the inputs to this logic circuit, you will have a 1 on the output. So now I have a little example as well, another one. So we have to determine the binary number for 1001 by producing a high level on the output. So we write down this, which we need, and then we say, okay, so this is must be a 1, and there must be 1, and that is a 0. So we invert only the A2 into the 4-input AND gate. So you have an AND gate with all the inputs, number of inputs, that's the number of inputs here, so it's 4 AND gate, and only when this code is passed as the inputs, it will be would be a high value. So now we're looking at a 4-bit decoder. In order to decode all possible combinations of 4 bits, 16 decoding gates are required. This type of decoder is commonly called either a 4 to 16 line decoder because there are 4 inputs and 16 outputs, or a 1 of 16 decoder because for any given code in the inputs, 1 of the 16 outputs are activated. A list of 16 binary codes and their corresponding decoding functions given in table below, which is on the next slide. And if an active low output is required for each decoded number, the entire decoder can be implemented with a NAND gates and inverters, which is important. In order to decode each of the 16 binary codes, 16 NAND gates are required. So now we have our binary inputs, our BCD number, and this is the decoding function, and this will be the output. Okay, so you can compare every single one. So if you want everyone to be 1, this will be your decoding output. And this decoder is an active low output. So you want a 0. Active low is 0. If it was an active high, then this would be a 1. So now I have a 1 of 16 decoder in IC form. It looks like this. You have the outputs. Here you have A0, 1, 2, 3 with input. You have VCC and ground. And then the cascading inputs here. So if you have more than 1, you will wire the cascading inputs. So what's all this for? So now we have an example of a BCD to 7 segment decoder. So this is what we want to get to. So this is a 4 to 1, 2, 3, 4, 5, 6, 7. Or if you have 8, 4 if you want to use a point as well. So now our BCD input, let's say it's 001, which is a 1, would be converted to a 0, 1, 1, and then the rest zeros. in order to light up just these. So this is what we use decoders for. So we decode the BCD number, and then on its output is the 7-segment displays input. So we wire this then direct to 7-segment display. So all we need to do is we send the BCD number, we don't have to do anything else to it, and it displays exactly the 7-segment. So this is what we want. This is why we're doing this. Okay, and this is just, the next video will be on the encoders and then multiplexers. Okay, good luck.